All right. So all this goodwill I'm going to negate now by asking, okay, how many people are actually using Python 3? Because async IO came up, and there was sort of this, I think Simeon's sort of like, so install Python 3, right? How many people, okay, good. So some people are actually using Python 3. How many people on Python 2 would like to try Python 3 but don't want to script their environment? Oh, ho, ho. So here's what I just did. When Simeon said that, I was like, you know what? Here's what I'm going to do. I'm going to install Python 3. I'm going to use Conda, which is the packaging tool inside Anaconda. I create a new environment, not virtualenv. Conda has its own environments, which are much, much, much better for when you have C libraries, native libraries, things like that. So I just said Python 3 is the name, Py3. Python equals 3.4, so that's the Python I wanted. Conda goes, hits Continuum's repo, and says, okay, well, here's what you're going to need at a minimum. Of course, tickle TK. Who doesn't like tickle TK? Anyway, so it downloads this, installs it, done. Now to activate this, source to activate Python 3. So I'm going to do here, source, activate, Py3. And I've got Python 3, right? Python. It claims to be Python 3. Let's try it. Yep, looks like Python 3 to me. Hello, Python 3. Yep, definitely Python 3. Okay, so the reason I bring this up is because I've done this now. Notice there's a little Py3 in front here. That means I'm inside the Python 3 sandbox. When I go and I say conda install NumPy, that installs NumPy, well, the latest one, 1.7, 1.8. It installs it against the Python 3, so it's the right one. And you can notice actually the conda, the build string here, it's build Py3 for build version 0. Boom, now I've got NumPy, right? So, and I can do this in all my bokeh demos that I was doing, still work, because that's in the bokeh release sandbox. So anyway, conda, there's a reason why some people in PyData and SciPy world are rabid about conda. And it's not because they hate pip, but it's just because some people who don't understand some of the pains that we go through on the PyData and Python, the scientific Python side, don't understand just like how much pip doesn't actually solve that problem for us. So anyway, this is a segue from one of the announcements, and then a segue from one of the talks in terms of Kalman filters. Back in the day, when I was at Enthought, my friends and I, in the heady days of 2008, 2007, we actually built a multi-touch device after Jeff Hahn's TED Talk and everything, diffuse IR, all this stuff. But a camera, we used OpenCV, wrote it all in Python, and had finger tracking, all this stuff like this. And to do this, to make the camera, the finger tracking stable, we had to use the Kalman filter. So there's a Kalman filter implementation here in Python that we'd written to do some of this stuff. So it can be done. It can be done very, very fast in Python. The key thing is this code was being run interactively real time off of video feeds coming off the webcam to track a finger. All right. So not just controlling blimps, but also before multi-touch was invented by Apple, we were doing this sort of stuff. So anyway, hope there are no Apple employees I offended here. I actually, of course, I use Apple products. So anyway, okay. So to my real talk then, let's get on with it. So this second talk that I'm going to give is about Blaze, which is another open source project we're doing at Continuum. It is again one of the DARPA-funded projects, the third one of the trifecta, right? Trifecta is the company. Trifecta is the actual word. So of the trifecta, the other one is Numba, which is a Python compiler. But Blaze, it's a project that's actually, it's been under evolution and a lot of experimentation. A lot of stuff has happened. It was one of the earliest projects we launched at Continuum, and there was a lot of experimentation. So you've probably, I don't know how many of you have heard of Blaze? Show of hands, how many people? Yeah, okay. So there's been talk of Blaze for a while now. And we've been doing a lot of experimentation in this area. And what we really wanted to do was say, okay, here's what NumPy provided for scientific and Python for data analysis. What are the really most important things that it did to allow this huge ecosystem to blossom? One, it was fast, but two, it was a data connector. It could describe people's legacy data formats. It could connect to C and C++ and Fortran code. It would basically serve as a good enough lingua franca about large data in memory for everything from scikit-learn and scikit-image to Python and Theano and all these various other things, all to be able to talk the same language. And that's actually really, really important. Ruby never got that, right? And so there's not really a Ruby for data kind of community. There's some people doing a little bit of work there, but not really significantly. Perl, there is PDL, but what gave rise to I think it's very, very important. This is an insight that took me, many, many years of consulting when I was at Enthought to finally come to this realization that actually Python people were using NumPy not because they had fast array math. If it didn't have fast array math, no one would use it. But they used it not because it had fast array math, but because there was the substrate of data description and large data computation and basically pointers to large data that could put Python in the same sort of level as C and C++ and Fortran, and also allowed people to write Python codes at the top above that level that would be very efficient. So anyway, that's kind of a lot of hand waving, right? My hands are really waving here. But Blaze is an attempt to take that and generalize it for now. Because NumPy, it started in 2006. My co-founder, Travis Oliphant, wrote NumPy to unify NumArray numeric. How many people here remember NumArray numeric? Not a lot of folks, right? Yeah. Those were dangerous times because there was a fork in the community, right? NumArray had some really great ideas, fancy indexing, some other stuff, but it didn't have a lot of features that numeric had. Numeric was the original thing that Jim Huguenin and, oh my God, I can't believe, yeah, there's a lot of like Paul Dubois, I think, some of these other people that worked on initially like saying, oh, we can override getItem to make an array object and be like MATLAB, you know? And that sort of legacy, you know, it really is a lot of MATLAB and Fortran thinking that goes into the design of NumPy itself. And the fact that it's been this performant and this good and this stable of a library for this period of time really is a testament to it. But we can see with the rise of popularity of pandas, right, that there's more that we need in data, in kind of in the Python data world. We want tabular data structures. We want labeled arrays. Sometimes we have nuns and nans. We sometimes have ragged rows and columns. We want to deal with all that. We don't have to write a lot of code to do the munging around it. And so Blaze is sort of a rethink. It says, okay, well, what do we really need now, circa 2010, 2012, 2014? What is the equivalent of a compute backend, like C or C++? What are compute backends? What is a generic data description that we really care about, that people are seeing really in production? And what is a good enough system to allow additional things to build on top of this, right? The intent is not to build a columnar database, because many people build very good columnar databases. The intent is not to build a NoSQL query engine, because there are NoSQL query engines out there. The intent is to build something, figure out something that can be a new lingua franca for a lot of the compute backends, the data query backends, and the front-end compute and data analysis sort of expressions all to meet and converge. And that's the motivation behind Blaze. And also, before I start, I would say the credit for this presentation goes to Matt Rocklin, a Blaze developer, core Blaze developer sitting right over there. He's the guy who said he wanted to use R. So once he's done with Blaze, we might let him build blaze.r. Okay, so this is to this point. NumPy arrays, pandas, data frames, these are foundational data structures, right? And one of the challenges is that they are limited in memory. You can do some memory mapping, you can load, map to HDF5 and all these other things. But fundamentally, being limited in memory, it's actually okay, because machines are getting very big now, right? The memory is growing really fast. But there's still a lot of cases when you want distributed, when you want to go out of core, and to have to completely leave this ecosystem that you're familiar with and go to a whole nother thing is kind of jarring, right? And so if you look, there's a number of different things here that do streaming out of core, distributed and whatnot, right? Things that are closer to the Python side of the world. Things that like, Petsy or Trilinos, which is a big C++ framework. There's, kind of a newer, smaller, more limited scope projects like Biggest. Elemental is a distributed array system that's written, distributed linear algebra and array system written for kind of MPI and C++ sort of things. All these are valid in different kinds of situations. They're kind of NumPy-like because these are array-like. And then the more data framey sort of things, you have like, of course, HDFS and the entire Hadoop ecosystem and everything that builds on top of that. There's things like PyTables and kind of Francesc's new project on a new columnar format called bcalls. And there's a number of kind of traditional SQL query engines that have grown more and more legs for doing data framey sort of things. But again, each of these is valid in a particular situation. But these are all completely different, right? Like trying to make Hadoop work with, Reveal fail. Okay, making Elemental work with like Hadoop is just like, how do you do that, right? Theoretically, Spark can be scheduled by Mesos, and Mesos works with MPI. Maybe that'll work with Elemental. No data scientist really wants to play there. Like, they don't want to go there, right? They just want the stuff to work. And so if you look again at data representation, so these are compute engines, but data storage, there's a number of different formats that everyone is always dealing with all the time. You have to juggle all these things. And each one does have advantages in each situation. None of these is like completely bogus, right? If it was completely bogus, it wouldn't make the list. And so like trying to learn how to use each of these pieces of technology, trying to learn not just how to use it, but when you shouldn't use it, right? As we all know in practice, Every vendor, every author of every library, myself included, will promise you the moon. And it turns out the moon is just in the next release, right? Or the moon kind of works if you talk to our consultancy, right? And they'll bring in some consultants that give you the moon. And so spinning up new technologies, really validating and saying, does this really work for my problem I need to solve like this week? That's very expensive. It's not really that agile to explore these things, because a lot of these things have different paradigms as well. So it's not just learning how to spell things differently, it's learning different grammars, different ways of thinking. And also, some of these technologies we listed, they've been around for a little while. There's new stuff coming down all the time, right? There's new stuff being created, being thrown out there, all sorts of stuff being created all the time. Even legacy systems or mature products are growing new sort of versions and new capabilities. And keeping up with that is a full-time job. And so then the foundation, right, a foundation around this stuff is something that can adapt over all of these things. It will be a glue layer, something that is sort of allows you in the face of this heterogeneity and this kind of blossoming, kind of just mushrooming field of technologies. It gives you some place where you can say, well, from here, I can try these things, I can play with each of these different things. And so Blaze, that's kind of, again, the vision of Blaze here, right? We connect familiar interfaces to a number of different compute backends. We have an abstract, there's sort of a few core things in Blaze. There's an abstract expression system with arrays and tables at their core. So I can write operations on these things, and those operations are preserved as expression graphs. And so if you think about what NumPy does, anytime you have any kind of expression, it actually creates a new array structure, right? It actually goes and makes copies. There's a lot of transient memory used even in one line of NumPy. And again, 95% of the time, that's okay. A lot of times, though, you just hit these edge cases where that just blows up your memory. So actually doing an expression system is closer to the functional languages like R and Julia. So we have an abstract expression system that lets you spell out what you want to do with arrays and tables. And then from these expressions, we can dispatch to different computational backends. And then the dispatch system actually kind of understands like what is storing what data, what backend has what data, how do I take this expression that's trying to do this operation on this piece of data and spell it right for that backend, and this other thing spell it right for that backend. And so, sorry, if you look at it, can everyone see that? Do I need to make this a little? I can't make it bigger. Oh, that's right, this is reveal, so you can't actually, all right, let's make it. All right. So anyway, so if you look at this, so this is first bit of code here from Blaze import star, which we all do, right? Import star is the right way to do it, right? Anyway, so that's a joke for everyone who's new to Python. Don't do import star except in examples. So now what we're going to do is we're going to tell Blaze. So CSV, capital CSV is a symbol in the Blaze namespace, and we just tell Blaze, okay, look, this CSV file, give me that data set, iris, okay? And so we create a table around it, and we're going to grab the first 3 elements out of the table. And you know what? Oh, Mac OS versus Reveal. Who wins? Here we go. Haha. I can make this a little bigger. Okay. So what happens here is you can see. Okay, now we're getting kind of the first 3 elements here, and you can see that actually just using the CSV, Blaze has created a table nicely, whatnot, and we can call things like okay, species, which is this column, the last column, distinct. What are the distinct values, right? So that's very nice. But if you look between these 2 slides, all we've done is said, okay, this is CSV, here is SQL, it's a SQLite file. And that's the table I want out of it. I want the iris table out of this SQLite file. Everything else just works. You don't have to change any of that code. And Spark, too. We tell it, create a Spark, use PySpark, create a Spark context. We're going to actually load the CSV into the Spark context. Now we have a table around this RDD. I don't know, if people are not familiar with Spark, some of these terms may be unfamiliar to you, but RDD is Resilient Distributed Data Set, and it's how Spark manages kind of distributed memory and distributed data. But what we've done here is we've mapped that RDD, which is Spark, and it's either hosted on distributed memory via Tachyon, or it's actually HDFS data. We just look at the head 3. Again, you write the same Python code, and you're hitting different compute backends. And right now, these are the backends that we have, and we can build more. And to build more, it doesn't actually take that much time to get a simple thing going. And if you look down here, like these are very, very disparate technologies, right? So HDF5 is a scientific data format. Like astrophysicists use it, right? Finance and quants, they use that too. But like, Spark and Impala are completely divorced and removed from this kind of technology. So like, all of these things, you have the same Python code that you can get all of these things. And the Python thing is the same thing. You can just take pure Python data structures. You have a list of dicts, a dict of lists, all of these things. You can do the same kind of query style, same kind of syntax. And so what we want to do is we want to organize some of these other open source projects to achieve this analytics engine that can talk to all of them and give you simple Pythonic expressions over them, right? And it doesn't actually, Blaze itself is not going and actually, ripping out the bits and querying them, comparing them, and all this other stuff. It's actually just doing sort of dispatch and some munging and some compilation and interpretation, but it's not actually going and doing what the backend engine does. It's really an orchestration around the stuff. So how does it actually work? Right? And the way it works is that we actually separate out the computations from the representations of the data. Those are two separate things that we can talk about in a first-class way. So if you look here, we create this symbolic sort of table that has this kind of schema. So we've created a schema, and we want to say, okay, this is a list of accounts. We have ID, name, and amount, and we want to find all the names of everyone whose amount is less than 0. Okay, so this expression here is what deadbeats is. Deadbeats is this abstract expression. It's very Pythonic. It spells very nicely. Anyone who's familiar with pandas and NumPy can write this. And then now if we create a data structure in Python that's a list of lists, we can just compute on it. We basically just, we can spell this out explicitly here and say, well, compute this expression on that data structure. And you get it. And we can still, again, keep the same expression, but instead of a list of things, maybe we have a data frame that we created. And we can compute the same thing on the data frame, right? And likewise with Spark. Okay, the Spark context, we get the RDD here. It's a parallel collection. Like, it's all this like Java stuff like spinning around the back in the data center. But all you write in Python is this. And it's the same code, the same expression. And again, the key thing here is that the Python data scientist, data analyst, only has to think about this level of stuff, because this is what they really want to express. This is the query they really want to express. And what you find a lot of times in data science scripts is this key, like the heart of what you're trying to get at, is embedded in about 100 lines of other crap. Like, there's no better term for it, right? It's other crap. I was involved years and years ago, actually, on a multi-million-dollar geophysics project, which at the end of the day was an attempt to build a huge UI, replacing a bunch of MATLAB code that was really about 100 lines of Python code, like actual science. It's just amazing how much, if you can actually separate out and distinguish and extract the science and the data kind of science from the data munging. And so we're trying to do it. It's a difficult thing. It takes a lot of art and pragmatism. And we're really trying to do something, I think, fairly bold here. So what this looks like, let me show you another practical example here. This is a notebook. And this is some data. This is 10 gigs of data from the Home Mortgage Disclosure Act. It's this big CSV file. It's 10 gigs of data. If you create a Blaze table around it, you can sort of see the kinds of data that is in this data set, right? This is probably not unfamiliar to people who do data for a living. Like, for people who don't do data for a living, this is sort of like, oh my God. Because this is 10 gigs of this stuff, okay? Anyway, so 10 gigs of this stuff. So now let's reduce it down, because there's a lot of columns, as you saw. We only want a few of them. So we're just going to say, well, T, we're going to grab these columns. We just want these few columns. Okay, so now we have a reduced data set, and we can see sort of the summary of the first 10 rows. And let's just find the ones that are in New York. Now, once we grab T2, this is just an expression. This is evaluated nothing, right? This is just an expression. And now what we're going to do is we're going to say, okay, for the values that are in New York, for the loans, the mortgages that are in New York, we're going to do a group by. So Blaze has this by primitive. If you guys do pandas or any kind of BI sort of data analysis, you're probably familiar with kind of group by and pivoting kind of concepts. So we're going to group by. We're going to group by the action taken here. So things like loan originated, application denied, so on and so forth. We're going to group by this. And what we really want is we want to do the count, how many there are. That's the aggregation function we want to use. And we're going to sort so it's descending sort of the most common actions, right? And again, before we did this cell, there was no real work being done except for some of the summary sort of generation. When we do this into, so this by is the group by, the into says, well, once you do this, I want you to return me a data frame. Turn it into a data frame. Now this is 10 gigs of CSV, and when we trigger the cell, we're going to sit there and wait a little while. as Python goes and crunches through the CSV, parses out each row, does this operation, does all of this kind of stuff in the back end, and then we get this data, which shows us, okay, the different actions and the different frequencies. But it takes a long time, right? Not so good. So now, let's say, okay, well, what if we take all this data and we put it into a SQLite file and see how much, because SQLite's actually pretty good technology, right? So let's just put it in a SQLite. Well, that's one line. Right, we just said, okay, here's a SQL file, which is this, create a new table called data. The schema is whatever came off that table that we inferred off of the CSV file. And just into this SQL thing, just put all of T into it. Okay, it does a little while, it takes a little while to do it, it does it. And now in SQLite, the representation is much more condensed. It's only 2.7 gigs. And now, let's do the same query, and it's only 7.46 seconds wall clock time, okay? And same data. Now, when we do later ones, we're going to have the exact same output, so we're not going to show the output here. But what we can do is we can go and also create an index. So we'll tell SQL to create an index on this data set. And now if we do this query, it comes down to 2 seconds. And let's say, well, how does Mongo stack up against this, right? Well, let's load into Mongo. There's your data load into Mongo, one line. I can't highlight, of course, so there's one line. And now we do the same query, and Mongo comes out 7.6 seconds. And let's give Mongo a fair shake and let it index as well. And it comes out actually faster than the SQLite, right? So you sort of look at, this is not particularly scientific benchmark, but it just shows you ballpark. And the key thing about this, this is all nice and everything, but the key thing about this is that you can do this. It was not a complete total pain in the butt to do this, right? It's one line to the data move, another line to create the index, and just play with it. And also, very importantly, I think many of you probably work in teams with other people. If you do some of this machinery and you tell other people, just write code like this, or you can write query code like this, and it's just going to work. Just edit that cell. Play with that cell, just ignore the other stuff, right? That's the kind of capability now that we're trying to provide in the Python ecosystem. So back to the other slides then. Another thing that we have in Blaze is this Blaze server. And what it does is it exposes the Python data, and it gives you sort of indexing semantics, all these things, via a JSON web API. And so you can basically really quickly spin up a data server, and it has many data sources that it can sort of expose to this web interface. So for instance here, I don't know if everyone can see that. Okay, we'll do it this way. So again, same examples before. We load up a CSV file, and we tell Blaze to create a server that's just on port 5000, and that server is going to have a data table in it, essentially called iris, which maps to the CSV data set. And then we can now query it through JSON. Just with curl, you can actually go and just query it, and it comes out with the data, right? But of course, you don't have to just use JSON. You can spell it out with Python, right? So here's using the quest library. We're hitting this, and we get the JSON dump through Python. But anything that can hit a web endpoint can get this data. You can hit it with Bokeh, because Bokeh is perfectly capable of making an AJAX request. And the other thing you do, if you start spelling things, if you start doing this with Blaze as the client, so we've shown how Blaze is the server, and you hit it with whatever web client. But if you use also, if you want to create more interesting queries, we have a support for that. So here, this query, the spelling is a little bit low level. But essentially, we're saying, okay, just give us this column. The operation is column, so give us column. And we want, out of this table, we want this particular column. And we get this column back. And if you don't want to be writing, all right, let's do this here. If you don't want to be writing your queries in JSON, you can do it from Blaze. So here, Blaze, we do expression by, the same thing, we want to basically find the minimum and the maximum for each species of iris in this data set. And what you can see what Blaze is going to basically do here, with the server, or the compilation infrastructure in Blaze, takes these expressions and turns them into this kind of query syntax, sends them to the server, and then we have a table that's actually this remote Blaze :/ array, and it goes and runs, we can grab the head, and then, how do I see, there it is. That doesn't help, does it? Okay, there you go. I want to show you that it's actually doing it here, right? This by function here, Blaze understands this is actually the remote data backend. I'm going to compile this expression, which looks like a function call, smells and quacks and looks just like NumPy or Pandas, but is actually going and sending that expression to the server side. It's running on the server. And yeah, so this is really, we're very excited about this. People talk about open data and sharing data and things like that. It doesn't help if sharing data means, oh, hit this FTP site, log in as anonymous, download 25 gigs, extract all the CSV files out of the 25 gig gzip, and then convert this COBOL format to columnar format. Like that's just, don't do that, right? Like that's just really bad. And we're hoping this kind of technology allows people, or will get people to do more of, here's my array, this URL, just play with it. Just play with it. And so here, now this is a CSV. We've loaded into a data frame, but you can actually have this be Mongo as well. So we're now sort of proxying queries against your Mongo uniform interface, right? The client is none the wiser. It doesn't know that this iris data set being represented or being served up by the Blaze server is actually backed by a really, really beefy, expensive, tangent-optimized Mongo installation, or just like someone pointed at a directory with a CSV file. And by the way, it's not just one CSV file. You can actually create Blaze arrays that look at a directory full of gzipped CSV files or whatever. It just does it. Okay, so anyway, that's all right. That's kind of. That's pretty much that. I guess if there's any questions, like the goal, again, the goal of the project here, and I know there's a lot to talk about, but the goal of the project is to figure out what is the pragmatic interface here that we can go between the data description, the schema, the data layout and representation, and the actual computation backends, and be able to talk about each of these things in a first-class way, and be able to kind of mix and match them and do the right things. And the URL for the project is blaze.pydata.org. You can read more documentation there. Yes? Refresh the slides. Awesome. Woohoo! We'll do it live. All right. I can refresh it. We'll do it live. All right. So here we go. Connecting technologies, users, right? Connecting technologies to each other. Really providing an interface. One of the things that I talk about actually in my PyData at Facebook talk, I really talk about let's see, PyData past, present, PyData SV 2014 keynote.zip key there. It's probably that file, who knows. Okay, and I talk about what Glue 2.0 looks like. Okay, I'm not going to waste your time digging through my slides. If you guys are interested, I can give the slide. You know what? I can do this talk at the bar we're going to go to afterwards, if you guys are interested. But the idea is that Python, people talk about Python as a glue language, it sometimes almost dismissively or condescendingly. But what it's turned out to be is actually, glue is actually pretty useful when there's a ton of stuff just all over the place. And we're interested in figuring out what does Glue 2.0 look like. Well, there's a lot of compute backends. It's not just data descriptions. There's different kinds of schema systems, different kinds of query systems, all these different things. And that's just the data representation and compute engines. On the front end, you have people writing deep learning algorithms and boosted gradient design and all this other stuff. Like it's all this stuff happening on the front end. These two people need to talk, these two camps need to talk to each other in not an N by M way, ideally in an N plus M way. And Blaze hopefully allows us to be kind of a common ground to allow that exchange to happen. So please go to the website, learn more about it. We're happy to have questions on the mailing list. The mailing list is getting very active now with people talking about all sorts of different technologies and ideas to bring in. No, Link, have you looked at SciDB? Have you looked at KDB? Blah, 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 all these various things. We love to have those discussions with people because we're very excited about the project. The DARPA funding is for multi-year effort. We're just kind of getting started on this stuff. And I think it's at a point now where we can start doing real work with it. So we'd love to hear from users. At this point, I'm happy to take questions about either of my talks, but I think there is there an announcement or anything else? I think afterwards we're going to go to the House of Shields. Yes. So I'll be there, happy to take more questions. If you guys want, I have my business card up here. Again, you can get in touch with me by emailing me or just on Twitter at Wang. But thank you very much for your time, and then I'm happy to take questions at this point.
I'm wondering about the SQL integration. How far could it replace an ORM? Does it follow foreign keys and stuff like that?
I don't think we have. Actually, I should get Matt up here too to answer some of the questions. But I think right now our SQL support is fairly basic. Is that accurate or?
It's rapid, depend on SQL Alchemy, essentially.
You get the.
Yeah, so currently we use a SQL Alchemy core layer. That's what Blaze depends on. Most of these things, I just sort of depend on some other Python library. We don't do this sort of, the ORM layer is nice if you have sort of many tables. Can you sort of think about all those tables at once in a nice way? I'm not saying joins, but I'm saying can you give me some other representation? That's what ORMs do. Blaze is doing that right now. Blaze is just taking sort of a pandas type interface and creating the right query. So maybe the right answer to your question is we're using SQL Alchemy core, not SQL Alchemy ORM. Does that speak to you, or okay?
What about JSON? If you
What
would you think about JSON documents? Because they can be nested, right?
Right. So the question is what
about JSON documents because they can be nested and so on and so forth.
Yeah. So in particular, I'm going to expand your question and say, what about things that don't fit into a tabular model? Would that satisfy your question? Yeah. Yeah, so there are other technologies that do satisfy that in the Python ecosystem or elsewhere. We haven't currently hit those. So things that I would use for that are just sort of basic core Python. We could put it into Mongo, right? Mongo could support those. And we could talk sort of tabular queries at Mongo, but we don't currently have the expressions to sort of drill down into that. We also have this project Dined, which is like NumPy, but is much handles sort of richer data sets much better. I think at the SciPy video, I would look at the Dined project. If there's a SciPy talk on Blaze, and Mark Wiebe, who works on that, takes a big giant, 40 gig or very very large JSON blob and interoperates it with NumPy, NumPy-like syntax very very cleanly. But so your question is, do we handle rich data structures? The answer is currently no. That's sort of future work.
So actually, yeah, there's a slide that shows basically there's a Kiva data set that we had that was a scrape of kiva.org, and it's like I think it was like 3 gigs or something of JSON. Actually, that was maybe is that the one you're talking about, or is it a different one?
It's annoingly large.
It's like 3 gigs of just JSON, right? And Dined was
nested, annoying.
It was deeply nested, all sorts of variability and variable length kind of stuff. Dined is able to basically process that and say, well, this is a this by nested by that by this is a variable dimension, like deep in the core. This is a variable dimension. These are strings of variable length, but this is a datetime. This is a Unicode. This is a thing I understand, right? And so it's actually able to handle that variability. One of the things to look at, if you look at the Blaze, the docs here, there's actually sort of this overview. This idea of being able to handle shape heterogeneity at the core, being able to handle some missing values, labeled arrays, things like that. Those are really things that we see as core to what Blaze should be able to do. And related to that question, though, is that every single one of these computational backends is going to be more powerful, almost, not by definition, but almost certainly they're going to be more powerful than what the generic expression over all of these things can be, right, at its core. So there may be things that Mongo can do. I mean, certainly there'll be things that Mongo can do that we're not going to really be able to express in Blaze. But the goal of Blaze is to figure out, try to grow the surface of common things we can express over a number of these back-end systems when applied to certain kinds of applications. So if you're using Mongo as a transactional store to back your big web application, you might not want to go through all the different, you might not want to go deeply nested in the document structure when you're actually doing the analytical processing on it, right? And so that's kind of and any really big, popular commercial thing we hit is going to have that kind of flavor, right? There's going to have some level of capability that's going to kind of roughly match the table stuff, and it's going to have some really cool stuff beyond that we're not going to have a generic expression for necessarily. And so that's something that we're just going to have to sort of figure out as we get there, I think. There may be ways to build extensions and so on and so forth. But right now we're trying to get that, what is the pragmatic, useful core that's kind of common across a lot of these things? Thanks, great question. Yes?
Really, really awesome graphics with Boki. But my question is, are you working on 3D and WebGL?
3D and WebGL, right. So there's 2 aspects of that. Right now we're not active. There's no one within the next 3 weeks that I know of on the project that's going to commit anything that uses WebGL. Okay, so that gives you some perspective. Within the next 6 months, I would expect us to have some WebGL experiments checked in, and there's a couple of projects that we're interested in, and also some other folks we're talking with about work in this regard. And actually, kind of also to the question about graphs back then, for doing large sort of graph data kind of things. I'm interested in using the GPU through WebGL to do some of those sorts of things. Really bright guy, Leo Majorovich. This conductor, Leo Mayoro. I don't know, is Leo here? So he just shows up in places sometimes. I don't know, just make sure. Okay, it's really creepy to talk about people when they're actually there. So anyway, so he has a cool project called Superconductor. It's sort of like been deprecated for other work now, but some of the work he's done here I think is very promising. And it's like stuff that we'd like to bring in. And then in terms of GL work, not WebGL, but just GL work. Bokeh is, I did say we want to do it for the web, but we also want to have a rich client backend eventually. And the project that I've been kind of in touch with and kind of keep an eye on for doing that is a project called VizPy. They were actually just, I think, this week on Hacker News because they had a new release. The guys that make it, some of them are acquaintances of mine. They're really good guys, and they think nicely about these things. And they want to provide basically an object-oriented Pythonic interface over OpenGL and GL shaders. And on that kind of infrastructure, I think it would be a nice way to do an interactive, workstation class, rich client sort of backend for Bokeh. Okay, I think we're out of time now. Thank you, everyone. We have to get out of here at 9:30. That was the other announcement I was supposed to make. We have to get out of here at 9:30. Thank you, everyone, for coming. I really appreciate all the questions. We're going to go to House of Shields. I really want to hear other questions and have conversations with all of you. So see you over there, I guess. Thank you.